Thank you so much, and thank you for inviting me to speak. So this is all of what I will be speaking about is joint work with Elena Pavlescu. And here is my plan for the talk. I'll be talking about contact geometry and Legendrian objects. So we're going to start out with just an introduction to contact structures, and then Legendrian knots. So this is what's sort of what we're generalizing when we work with Legendrian graphs. And then I'll talk about generalizing the standard invariants that are around for Legendrian knots, and then some of our results about Legendrian graphs. Okay, so with a contact structure, we're going to always be working in R3 for this talk. And what you're going to want to imagine is at each point we have a plane, which is contact plane. And so this is one example of a contact structure on R3. And this is going to be the one we're going to work with the whole time today. So here's our definition. If we have a 3-manifold, then we have a plane field, C, on our manifold M. It's called a contact structure if C is a kernel of a 1-form alpha, where alpha wedge d alpha is positive. So this means it's nowhere integrable. So what you want to imagine is something where there will never be a surface that is tangent to the contact planes. That's what's really happening here. And the example that we'll be working with is the 1-form. Ooh, I tried to use the thing. Back. Okay. Is this 1-form? So this is alpha dz minus y dx is a standard contact structure on R3. And the standard contact structure, so contact structures fall into 2 categories. They're either tight or over twisted. And this is the one tight contact structure on R3. And this is really where things get interesting, is in the tight contact structures. And the over twisted ones are sort of, somehow they're floppier, they're less rigid, and they're easier to understand and to categorize. And so, just for your information, so okay, so like I said, this is the one we're going to be working with. This is our standard contact structure. And so, important thing. So we're working with the kernel of dz minus y dx. And so each of these planes is going to be the span of d dy, and we have d dx plus y dz. So you see, like, along the x-axis, they're all parallel. And if you go up and down on the z-axis, they look exactly the same. And as we go out here, it's turning this way. And as you go into the positive y direction, it turns this way, away from us. So this is an example of something that's tight. And then for an over-twisted contact structure, what that means is that somewhere in the contact structure, there's what's called an over-twisted disk. And this is an example of an over-twisted disk. This is a disk where all along the boundary, it is tangent to the contact structure, to these planes. And so this is the other thing that can sort of happen. A tight contact structure is one that never has an over-twisted disk. Okay, now we're going to move on to talking about knots, and so objects in these contact structures. So everyone is familiar with this. We have our nice pictures. So we're working with an embedded circle in R3. And then what we're going to be working with are what are called Legendrian knots. So this is a knot in our standard contact structure, and where at each point it is tangent to the contact planes. So the tangent vector, the tangent vector is in the contact plane at each of the given points. So you see, here's an example of the unknot, and you see it's everywhere tangent to the planes. You see a few examples of the planes there. Now when we work with these, we always work with the projections, right? And in this structure, there are a few different options we have for projections. You can work with what's called the front projection. So this is projecting onto the ZX plane. So this will look like this is an example of a front projection. And you can also work with what's called a Legendrian projection, and that's projecting onto the XY plane. Today we're really just going to work with what's called the front projection. This is nice in a number of different ways, so we'll talk about that now. So when we have the front projection, since we're projecting on to the ZY, or I'm sorry, the ZX plane, what happens is, right, for our standard contact structure, it means that this is in the kernel. So this is set equal to 0. So when we project, what happens is we have that y equals dz over dx. So what happens is the slope of your knot actually tells you what the y coordinate is. So we don't lose any information because we can see from the slope how far it is back. And we always imagine we're standing right here looking down the y-axis. So the y-axis is going into the board. So then when we have this, we have that y is the slope. So in this front projection, there are no vertical tangencies. That can't happen. So what we end up is we have cusps when you come to the sides. And since we're looking down the y-axis, we have that the overstrands are always the ones with the smaller slope. So they're always these ones will always be over because we're always imagining the y-axis is going into the board or into the thing. So here are two examples of front projections of knots here. So we have an example of the unknot, an example of the trefoil. This is the right-handed trefoil. So, ooh, what'd I do?
Sorry.
Oh, okay. I didn't do that. All right. Whew. All right. Right. So the front projection is really nice because we know if we draw something like this with cusps and with the crossings like this, we know it will actually be a Legendrian knot. So this makes it simple. Okay. And then just like with knots in R3 without the extra structure, when you have two Legendrian knots that are in the same knot class, they are related by Riedmeister moves as well. And so these are looking at Riedmeister moves in the front projection. This is the front projections of the moves. So this is what's allowed. So you have Riedmeister 1. And so this is the only way that it works because we have to have this overstrand like that, right? And then 2 and 3 looks pretty normal. So now, I feel like I'm going fast.
Can you go back a slide?
Yes. Oh, yes. Forward.
That one. So Riedmeister 2.
Yes.
That strand is way in the background.
Yes. You have to right. Okay, so yeah. And you can do the same with the other one, with something way in the front, right? If you have the other cusp. Yeah, and this is actually when, over here is when we would put the video. So maybe we should do that. So this is a video, and maybe it will work. So this is so you can see it starts with the front projection, and then you can see how the structure actually is in space. So here's our right-handed trefoil, but you move around. And so that goes through the Lagrangian projection too, the one with all the circles. Will you do it again? Yeah. This is our front projection. It's our Lagrangian projection. Okay. Thank you. Okay. All right. So with Legendrian knots, there are two classical invariants that people use to distinguish them and understand them. And the first one is the Thurston-Bannequin number, and then we'll talk about the rotation number. So the Thurston-Bannequin number, it measures the amount the planes, the contact planes, are twisting along the knot. So this doesn't depend on the orientation of the knot, because you're just measuring the number of times the plane turns around. So as you go all the way along the knot. So it has to be an integer. And the way you compute this is, if you go along the knot, what you want to do is you take a vector field that's transverse to the planes. So then you can push off in that direction, transverse to the planes, and get a push off of the knot that we'll call K prime. And then the Thurston-Bannequin number ends up just being the linking between your original knot and this push off transverse to the planes, because that will measure how much it turns around, because you get linking 1 when it goes around exactly 1 time. The other reason why the front projection is really nice is that we'll be able to have, both for the Thurston-Bannequin number and for the rotation number, we have a diagrammatic way to calculate it. So for the Thurston-Bannequin number, you can calculate this by just looking at the rise in the front projection minus 1/2 the number of cusps. So this makes it easy. And remember, I think everyone here is familiar with what rise is. So, and this is your signed guessing. Okay. So then the rotation number is a little bit more complicated. And what you imagine here is, if you take the tangent vector to the knot, you want to know how much that tangent is going to turn around in the contact plane. And what makes this challenging is because the contact planes are also moving, right? So we need to actually take to define this properly, you have to take a trivialization of K along with the contact planes. And to do that, you have to work with a ciphered surface to be able to properly define this. So this is a winding number of the tangent to your knot. But here, again, in the front projection, we have just a diagrammatic way we can compute the rotation number, and that's 1/2 the number of down cusps minus the number of up cusps. Okay, so should talk about what does that mean. So we have our cusps, and this is going to depend on orientation. And so if you have a cusp and it's oriented this way, this is going to be intuitively, right, this is a down cusp. And then if we're oriented the other way, this gives us an up cusp. So let's look at a couple examples just to do this. So here's the simplest unknot. This is the one we saw before. So now Thurston-Bannequin number, this is the rise minus 1/2 the number of cusps. So here the rise is 0, and we have 2 cusps. So we get the Thurston-Bannequin number is -1. And then the rotation number is up cusp minus down cusp. So if we look at this, we have an up cusp here and then a down cusp here. So we get rotation 0. Now, if we look at this, if we add, this is what's called a stabilization. When you add something like this, this is a stabilization. And this here, if we look at this unknot now, the Thurston-Bannequin number is going to be, the rise is still 0, but then we have minus 1/2 the number of cusps. So here we have 1, 2, 3, 4, so we get -2. And then the rotation is 1/2 the number of down cusps minus the number of up cusps. So we look at this and we have 1, 2, 3 up cusps and then 1 down cusp. So we get rotation of -1. So one thing that you see here is you have 2 different unknots. So they're the same topological knot type, but they're different Legendrian knot types. So the rigidity of working in a contact structure and having a Legendrian knot means that you have, for each knot type, topological knot type, there are many Legendrian knot types. And you can see that, in fact, adding a stabilization changes our Legendrian knot type. So we can always do that because we see that that's always going to change the TB by 1, right? Because you're always going to add 2 cusps, so you're always going to subtract 1 if you do that.
So you can't move from the bottom unknot to the top unknot staying within Legendrian knots.
Right. Yeah, yeah. These are different. Okay. Okay.
Is there a knot with those same TB and root?
That is not the unknot?
Yes.
Yeah. But this is, okay.
Sorry.
Now we're getting fancier. So this is, yes, there are lots of things that are in other knot classes that are, but actually the unknot is special in that TB and rotation completely determine it. So this is the only unknot with these TB and rotation, and we'll come back to that. Okay. Yeah. So one last one. Let's just go through this so everyone feels comfortable with TB and rotation. If we look at the right-handed trefoil, this example here, then we look at the TB. This actually has rise. So you look at this, these all end up being like this. So these all end up being, what, they must be positive crossings. And then yeah. So these are all positive crossings. So we get +3, and then we have -2. So we get a TB of 1, and then you look at the rotation, and we have to work with down cusp minus up cusp. So we have an up cusp, and down cusp, down cusp. So here we get 0. Okay. Now, there's a relationship between the Thurston-Bennington number and the rotation number and the Euler characteristic of a ciphered surface for the knot. So this is a result of Ellie Ashberg, and it's a classical thing in Legendrian knot theory. So if we have a knot in our standard contact structure and we have a ciphered surface for it, then the TB plus the absolute value of the rotation number is going to be less than or equal to negative the Euler characteristic. And so in the case of, this is not always sharp, but in some cases it's known to be sharp. So for example, with the unknot, right, we can find the negative Euler characteristic is going to give us -1 on the right-hand side. And so then if we go back and we look at this example here, this is one where the bound is sharp, right? TB plus rotation gives us -1. And what we see then is that this is the largest the TB can ever be. So that's the maximal TB, is that example there. And the TB can be made smaller, can be made arbitrarily small by adding these stabilizations. So if we take this example and we just keep on adding more and more of these, right, we will get smaller and smaller TB. So this special one, the special unknot, we call the trivial unknot, which is the one that has the maximal TB. And we'll be coming back to that as well. Okay.
So the left-hand side is, do you get different value of the left-hand side for different Legendrian type? Or is that invariant or not type?
Oh, yeah, you can, so you can make this can end up being smaller, but even for the unknot, right? If we
TV plus absolute value of rho.
Yeah, will change. So if we look at this is a special example, huh? This one is the same. Okay. So yes, there are examples of things where you don't have this. This is not sharp. And you have examples where this is strictly less than the negative Euler characteristic that you have in that case.
My question is, if you have a different Legendrian knot type of the same knot K, the left-hand side changes? Or
Yes, it can change, yes. Okay. So now we're going to talk about Legendrian graphs. So everyone is familiar with a spatial graph is an embedding of a graph in R3. And now we're going to work with the object of a Legendrian graph. We're just going to be working with this in the standard, with the standard contact structure in R3. And so a graph in R3 is called Legendrian if it is everywhere. It's going to be everywhere tangent to the contact planes. So all of the edges are going to be Legendrian arcs. These have actually shown up in contact in some contact theory before in proofs of theorems. So Giroux's theorem, which is a very important fact about the correspondence between an open book decomposition and the contact structure in a three-manifold, uses Legendrian graphs to get this correspondence. Also, this work by Eliashberg and Fraser showing that the Thurston-Bennequin number and the rotation number determine the Legendrian unknot. This also uses Legendrian graphs. So these have been something that people have used as a tool in contact topology for a while, but no one has actually studied them in their own right. So we're working on sort of laying the basis here to be able to look at them more carefully and then use them as a stronger tool. That's the plan. Okay. So the very first question should be if you will always have a Legendrian realization. So for all, if I'm given a spatial graph in R3, can I Legendrian realize that? And the answer to this is in the positive. So for any spatial graph in R3, we can Legendrian realize this with a standard contact structure. And with our Legendrian graphs, we'll also work with the front projection. So just like the projection we were looking at with knots, so here again, we're going to have no vertical tangencies, so we'll have cusps, the ends. And in the same way, crossings will be just as before. At the vertices, what's happening is these are all going to be tangent to the same contact plane that vertex is in. So just like with Legendrian knots, we have Reidemeister moves. So you have the same Reidemeister moves 1, 2, and 3. But then there are also additional Reidemeister moves to see what's happening around the vertices. So we have this, we'll call 4, where you can sort of slip the vertex along this edge coming into a cusp. And then also it can move out of that. We can take an edge and move it past the vertex. Right. And this has like a very positive slope, right? So it's really far away behind that. So that's why we can move it past. And then this one, this one is where we're just taking and we're moving this edge along the vertex in the contact plane. And I think this one is a little confusing because we're looking in the front projection. So it looks a little bit like you're changing the order of the edges around the vertex, but you're not because of what's happening in the front projection. So right. So the more negative are closer to us. So what's happening is this is coming out to us. And then we have this one. And then this one's like far away. It's like going back. In the same way, right? The more negative is closer to us. So this is closest to us. This is coming out. And then we have this. And this one is the most far away. So, so we number this like 1, 2, 3, 4, 5, 6. And now if I look down in the contact plane, what's happening is I have this is 1, and then my 2 and my 3, and then 4, 5, and 6. It's like this. So when we do this move here, where we take this edge and we're just moving it a little bit around the vertex, it's going to be behind here because this is like we're taking this 3 and we're moving it to the other side. So we're just taking this and we're moving it like that. And so you see it ends up being here, and this just has to do with the projection we're working in. But everything ends up staying, you have the same cyclic ordering around the vertex. Always is going to happen for a Legendrian graph, because it has to always stay tangent to the contact plane. So they can't actually change the order around the vertices. And here we're keeping the order around the vertex. And the fact that it looks a little different just has to do with the projection we're working with here. Okay. Wow. Okay. So then we extended the Thurston-Bennequin number and rotation number to Legendrian graphs. One of the important things to notice is that if you look at the cycles in the graph, they aren't going to be smooth like a Legendrian knot. They're only going to be piecewise smooth. Because what can happen, so if I have my graph and I have something like this, so if I look at one of these cycles, say if I'm interested in this cycle here, at the vertex, it has something like this happening. So it has a point where it's not actually smooth. So to define a TB and rotation number, first we define it for a piecewise smooth Legendrian knot. So we extend it in this way, which is actually very natural in the case of the Thurston-Bannequin number, because we took this push off and then the linking number. So this can be done immediately. It's exactly the same. But the rotation number is more subtle. You have to be a little bit more careful with working with something that's only piecewise smooth. Then, for the Legendrian graph, we define the Thurston-Bannequin number and the rotation number to just be the ordered set of the TB for the cycles. So you have a list. And the same for the rotation. It's the ordered set of the rotation numbers for the cycles. Okay. Now, remember our favorite unknot was the trivial unknot, which is the one with the maximal Thurston-Bannequin number. So this is this one. And Monk proved that the Bromian rings, as well as the Whitehead link, cannot be Legendrian realized where all of the components are trivial unknots. You'll always have to have one component with a smaller Thurston-Bannequin number. So it cannot be realized in this way. So we ask the same question for graphs. So we ask, under what condition does a graph have a Legendrian realization where all its cycles are trivial unknots? So when could we realize a graph with all of its cycles like this? And we are able to show that a graph G admits a Legendrian embedding in the standard contact structure with all its cycles trivial unknots, if and only if G does not contain K4 as a minor. Okay. So this characterizes this with a single graph actually in the obstruction set. I'm going to talk about the proof in one direction. I think it's a very nice proof, and it's also it works with similar ideas to what you use when you do prove things about intrinsic linking and intrinsic knotting. So okay, so we'll need two lemmas to work with this. The first lemma says, if we
question.
Yeah.
So if something is realized, then it's just a planar diagram without any crossings.
Oh, in general, it could have crossings, but for this, in this case,
Yeah,
right?
For this,
Yeah. In this case, you must have something.
Converse is true also. Converse is also. Yeah. Okay. Thank you.
Okay. Yeah. So for the thing you were. I mean, we can't have this. This is not allowed, right? So this has TB equal to -2. Okay. Okay. So we'll need two lemmas. The first lemma says that we're just considering an abstract graph, and if we look at two different front projections of this abstract graph, that they're going to be related by a finite sequence of Legendrian isotopies and changes that either involve one edge or two edges. So this is not staying in the same Legendrian class. We're imagining we just have two different Legendrian embeddings of a graph. And we're saying that I can get from one to the other by, of course, Legendrian isotopies. That's if they were in the same class, then we'd be done. But if not, I'm allowed to do, there are two other kinds of moves that will get me from one to the other, these changes. We could change one edge, and we could add in stabilizations. We know that's going to change the Legendrian class. And we could put change the crossings of the edge with itself. Or we could change two edges in this way where we change the number of crossings between the two edges. Okay, so this is just saying that if you have two different embeddings, this is all I need to do to be able to move between them.
So can you give an example of change B?
Change B?
Yeah.
So if I had something where I had something like this, maybe I would need to change this to be something like this somehow. You might, so first you would have to add the stabilization, but
there is no change in the number of questions.
oh, well, you could also, sorry. Yeah, that was sort of a more exciting but unnecessarily exciting example. Here we go. Better example. One, whoosh. Yeah. So we could change. Boom. This is a change of type B. This changes the class. It changes the knot type, Legendrian knot type. This lemma is not talking about staying within the same class at all. Okay, so a little different than what we usually think about. Okay, and our second lemma, and this is like the key. This is our key lemma to what we're doing here, is that for any Legendrian embedding of K4 in the standard contact structure, if we sum up the Thurston-Bannequin numbers of all of the cycles, this will be 0 mod 2. And here's how we can see that. So there are 7 cycles in K4, and if we have it labeled like this, out of 1, 2, 3, 4. Oh, okay. We have 4 3 cycles and 3 4 cycles. Okay. And each edge appears in 4 different cycles, and each pair of edges appears in 2 different cycles. So now we're going to choose this really nice embedding here. And in this really nice embedding, there are 6 cycles that have the maximal Thurston-Bannequin number of -1. And then there's 1 cycle that has a Thurston-Bannequin number of -2. That's this one right here, whooshka, like that. So we have a writhe minus 1/2 the number of cusps, so we get -2. So then, when we look at our sum, we end up with a Thurston-Bannequin number equaling -8. Now, we take some other Legendrian embedding, any other Legendrian embedding of K4, and using lemma 1, we know that this new embedding will differ from the projection of our original one by either Legendrian isotopy or changes in one edge or in 2 edges. If we have Legendrian isotopies, this won't change the Thurston-Bannequin number. This is an invariant. But if we do a change in one edge, what will happen? If we change one edge, we should note that 4 cycles contain the edge that's going to be modified. So this is going to result in a sum that has the same parity. So And in the same way, if we have two edges, these will appear in exactly two. Where did it made in blah 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 blah? Yeah. So this appears in exactly two of the cycles. So then, when we modify it, we're going to end up with something with the same parity again. So we see that the sum will always be 0 mod 2. We'll always have an even parity. Okay. Now, the main theorem. So we said that a graph has a Legendrian embedding in the standard contact structure where all of its cycles are trivial unknots if and only if G does not contain K4 as a minor. And so if it does contain K4 as a minor, then it will contain a subdivision of K4. And if we look at the cycles, the 7 cycles, then we see, if these 7 cycles all had maximal Thurston-Bannequin number, so they all had Thurston-Bannequin number -1, then the sum over those cycles would give us -7, which would not be 0 mod 2. So one of them must be something that is not a trivial unknot. And so that completes this proof. And the other direction is constructive. And it has a lot, it's a constructive algorithm given such a graph. And you have to look at a number of cases to do it. This, if you think about what we did, it didn't necessarily rely on it being an unknot. It just relied on the maximal Thurston-Bannequin number being odd. So this direction you can do more generally. We can really say something about embeddings where you're just looking at all of the knots having maximal Thurston-Bannequin number of an odd, that's an odd number, and that if you contain a K4, then you're not going to be able to have such an embedding. Okay, I'm going to talk about one other result. So this will go back to actually Elizabeth's very first question. So there are certain knot types, topological knot types, where the Legendrian classes in that knot type are completely determined by TB and the rotation number. So you know it's an unknot and you know what the TB is and the rotation number it is. You know exactly what Legendrian class you're working with. So the unknot is one of these, right? This was done by Ellie Ashberg and Fraser. This has also been shown to be the case for torus knots, the figure 8 knot, and that was done by Ettenmeyer and Honda. And it's also been shown for links that consists of unknots and cables of unknots by Ding and Jing. So, so we asked the same question: if we would be able to find a graph, and then we also have to take a topological type that we're working with for that graph, and have the TB and the rotation determine the Legendrian type in that case. So we haven't quite been able to find this. What we can do is we worked with 2 different graphs. We looked at what's the lollipop graph. Ooh, I'm out of space. So we looked at the lollipop graph, which is very, very simple graphs. We looked at 2 very simple. We looked at this and the handcuff graph. And we're working with what we're calling topologically planar graphs, which means you should be able to, if you're allowed to move it by ambient isotopy, you will be able to embed it in the plane. And in this case, we can show that for the lollipop graph, there are exactly 2 Legendrian isotopy classes for the topological planar Legendrian realization for a given pair of TB in rotation. So if you know it's topologically planar and you're given a TB in rotation, then there are only there are exactly 2 possibilities. And similarly, for a pair of TB in rotation, there are exactly 4 Legendrian isotopy classes for the topologically planar Legendrian realization of a handcuff graph. So in the handcuff graph, I'll show you how these differ. So if you're told the TB in rotation and you know you're working with a topologically planar graph, these are the 4 possibilities, and it has to do with what's happening around the vertices. It has to do with the order of the edges around the vertices. We know that will change the Legendrian class that you're in. So there are these 4 different possibilities. Okay. All right. So that's all. Thank you very much.